so, right? Visible?
Yes, we can. Yes.
So I was invited here to speak because I won this year's image award with the image that you can see here in the background. Of course, I will talk a bit about this image later on in my presentation, but I will use this opportunity to talk about my research and talk about what our research group does. So a little outline of my presentation is I will first talk about what our group does with the low energy electron microscope. And then I will give you the motivation for the research that I will show, namely the technique that we are developing, which is called optical near field electron microscopy. I will explain everything later what that means. And for that we need to do some experiments, of course, and I will show some experiments on antimony grown on silicon 111 surface. So first, let me explain to you what our group does and what kind of machine that we use to do all of our experiments with. So we have a low energy electron microscope, which is basically a reflection microscope where we accelerate electrons with 15 keV, and then at the sample, we slow down these electrons to a tunable voltage between 0 and 100 volts, so that we can have a low energy interaction with the sample. And then these electrons are then reflected back and collected into to our detector. They're accelerated back to the 15 keV so that they go through the optics and are collected here. Our beam is like 5 microns wide, so the field of view of one image is really 5 microns. So we see one image in one go, and it's not scanning or anything. We really have a video rate imaging. So to show how this looks like, well, we can do, of course, real space imaging. So that's this image over here, for instance. This is a stitched image of many images together to get this big overview of the silicon surface. And to the right is actually the diffraction image, the diffraction pattern of the same material. So for one image, I would say. And basically, the diffraction image is made up by all the electrons that are reflected, but at a different angular location. So we see the first order peaks. It is slightly distorted in our diffraction plane, but we see these first order peaks here, and here. And then all of these other peaks that we see are the so-called 7x7 reconstruction of silicon, which I'll also explain a little bit later on. So with the lean, we can switch between these two modes with the push of a button, which changes excitations of these lenses here. And so we can almost simultaneously measure like the real space image and at the same place also take a diffraction image. Now, one of the powerful things that we can show with the lean is that we can also tune this landing energy. So at a negative energy, the electrons are reflected back without interacting with the sample. And then at 0, they start to interact with the sample. And then with higher energy, they start to have still some energy left where they interact with the sample and then are reflected back. So and then if we take an image at every one of these energy levels, we can make a movie out of this. And that is, if I click now, yes, then you can see that this changes the image. So these are a stack of images basically, and at each image is at one specific energy. So we can see that this is very surface sensitive because it really depends on how many layers of material there are, what kind of response for these low energies we get. Now, this particular sample that this movie that I show here, let me try to play it again, is copper on graphene, sorry, the other way around, of course, graphene on copper, where we have a different number of layers of graphene. So here on the right side, you see the response at each of these locations. And we can see that there is a difference mostly here at this dip here at 3 electron volts. The dip here at 3 electron volt is actually an interlayer state of the graphene between the two layers. And then we can see the hybridization of this when we add another layer to the material. So one dip goes to two dips for 3 layers, and this is for 2 layers. Then we have 4 layers, and then we have 5 layers with every time an extra dip in this spectrum. So this is a very powerful tool to inspect these surfaces with. Another thing that a colleague of mine is working on mostly is that now if we don't have the gun on the backside and looking at reflected electrons, so instead of having this gun here, we can put a gun on the other side, which is not that easy to do, but we have done it. And then we can also shoot electrons through the sample with this low tunable energy. And if we do that, then we can do a reflection image on the left here, the lean, and then we can have the same area and do a transmission image on the right, which is TEM. Now, and also you have the same tools of spectroscopy where we can tune this energy and obtain characteristics of these single, double, triple layers of material. Now, this is all what our group does. And now I want to go to what my research is about and what my project entails. So this is also a similar type of. We'll also do something transmission, but it's a different concept. So my project is about developing this new microscopy technique. We call it ONEM, which is Optical Near Field Electron Microscopy. And in here we will try to combine light optics with electron optics to try to have the benefits of the best of both worlds, basically the benefits of both. So of course, electrons do a lot of damage to biological samples and a lot of other samples, or it changes the chemistry inside the liquid. So it is detrimental to have electrons at some of types of samples. So if we would have no electrons there, that would open up a lot of possibilities to measure on different types of samples. And then we want to keep, of course, the high resolution and the speed of the electron imaging that we have in the lean. So in this combination, it also opens up the possibility, like I said, with in liquid imaging, where we only illuminate with visible light, and we don't have any electrons in there, so we can also do in liquid stuff. Now that is the main benefits that the technique would have. Now, how does it work? How do we plan to make it work? And that is in a couple of steps. So we have an illumination here from the backside with visible light, and inside a liquid cell or some specimen is in there. And then in the very near field of the sample, so where the resolution of the optical light interaction with the sample is not yet lost, we already placed the liquid vacuum interface and then the photocathode. So the liquid vacuum interface should be something like graphene, a very thin layer. And then the photocathode must be grown on this side, which converts the photons in the near field back into electrons. So we continue on with the resolution of the electrons, which is of course nice. And then these electrons can be then imaged with lean again. So what do we need to make this work? We need a lean, well, that we have, and that is already working. But now my project is more about getting the other parts also working and involved. And today I want to mostly discuss this low work function photocathode that will convert the photons into electrons. Yes, so that is the concept of ONEM, and now I will continue on why we want to grow antimony on the silicon. So the antimony is a component of a low work function photocathode. It's a candidate material basically for us, which is potassium, cesium, and antimony. And we would like to grow this on graphene layer to have these least distance between the sample and the photocathode, because a resolution of this ONAN project will basically decay linearly with the distance to the sample. Um, so this we try to do pulse laser deposition, which I'll explain in the next slide what it is. But that in the Brookhaven experiments in Brookhaven National Laboratory in the beamline there, from a crystal made out of this material, only yielded the antimony from the crystal and not the potassium and cesium. So the strategy now is to grow antimony separately with PLD and then evaporate, co-evaporate the potassium and the cesium. So we're not there yet, but we have started on PLDing antimony, and we're investigating how that goes with our system. So what is pulse laser deposition? Pulse laser deposition is basically you have a very high power laser which emits short energetic pulses, and they are hitting a target here, and from that target it heats up locally at each pulse, and it ejects a plasma plume that is directed towards the substrate, and then the material at each pulse, a little bit of material is absorbed onto the surface. It's a very precise technique where you can tune the amount of material that you want per pulse, almost. So for that, there's a couple of parameters that we can adjust to get the right amount of material onto the surface. The most important one is, I guess, the fluence, which decides how much material comes out. This is dependent on the spot size, which we can tune with lenses, and energy per pulse, which we can tune with the voltage of the laser, basically. And then the second parameter is the substrate temperature. So depending on how hot or how cold it is, a different amount of material will stick to the target, to the substrate, sorry, and a different amount it will also grow in a different way depending on the substrate temperature. There's one parameter which is hard to adjust, and that is the targeted substrate geometry. In this image here, I show a different chamber where the geometry is ideal, as in you have a plasma plume which always is perpendicular to the target itself, the target geometry, and then there's the substrate which is also perpendicular to this plume. But in our situation, it's more like that the substrate is more like this. But no matter, it still seems to work fine, so that's good. Now I have to explain a little bit about the system that I have chosen to investigate this with. So basically, the goal of measuring this on silicon is to get some feeling for how PLDing of antimony works, and if it evaporates well, if it grows well onto a surface. And for that, not the most simple, but one of the simplest systems is then the silicon, just to grow it on a silicon wafer. Well, silicon is not that simple. As I already showed you, this diffraction pattern, as you see here, is actually a 7x7 reconstruction, and the atomic structure of this, it looks a little bit like this. So there is basically a gap every 7 unit cells of the silicon. I will explain now the reconstructions more in depth. So these reconstructions can be anything from holes or attributes onto the surface, but also the atoms reconstruction. So from the ideal lattice, they will deform a little bit in periodically, and that gives us these reconstruction spots. Go a bit more in depth in how these spots are formed. So these surface reconstructions, like I said, are larger periodicity. So they're superstructures on top of the crystal lattice with a larger periodicity. So say that this is the lattice. The lattice is here, hexagonal lattice. Then at every square root 3 by square root 3 spot, so that is one over here, there's an additional periodicity that, which can be a hole, or it can be that the the atoms in that direction are just a little bit closer to each other. And then if we turn this around and go to a reciprocal space, so the diffraction image, this would mean smaller distances. So we have here the reciprocal lattice, the one by one lattice, and then the square root 3 by square root 3 pattern would be the spots are here closer by. Two more examples of this type of reconstructions. So this one we will see soon in this antimony silicon structure is this 5 square root 3 by 5 square root 3 pattern, where additional to the square root 3 spots, you have another 1, 2, 3, 4, 5 spots that are visible. Well, these two are not so visible, but it really depends, because of these low energies. It really depends on at which energy you are measuring. So these this is a lead pattern with 24 electron volts, and if you change the energy, you will change the visibility of these spots. And on the right here, we have this silicon 7 by 7. And 7 by 7 is really that we have 1, 2, 3, 4, 5, 6, 7 spots between the 0th order spot and the 1st order spot. All right, now onto the antimony silicon structure. So it is actually not so simple. There's a couple of reconstructions, different reconstructions that can form depending on the coverage of the antimony onto the silicon, which is between 0 and 1 molar layer. So it's not that we can grow into more monolayers in a crystalline way. And it also very much depends on the temperature at which you deposit the material. So at high enough temperature and at the right coverage, these reconstructions will form on top of the silicon surface. If we grow higher than 1 monolayer, everything that is added is basically amorphous until now, at least in the results as well. There's actually a paper from 2002, so they already did these experiments earlier on with thermal evaporator, not with POP. All right, now the starting point basically of my research is this image where won the award with, is that we have now here a very clean silicon surface, where we see, if let's see, we have here these lines, these little bit better in contrast visible lines here, and also the similarly here in this direction, which are basically the atomic terraces of the silicon that we can see. And then in between, there's also these lines here, which are basically the domains of the 7 by 7 reconstructions that can form a little bit more in domains. Now, how do we obtain this surface? We obtain this by basically taking a piece of silicon wafer and then flashing it to 1200 degrees inside the lean, which basically burns off the oxide layer. And what is left is a silicon layer, a silicon surface without any oxides on there. And then above a certain temperature, so that's 860 degrees, below a certain temperature, that's 860 degrees, it will form into this 7 by 7 reconstruction. So what we do is we flash it a couple of times to 1200 and then cool it down, and then what is obtained is this. These two black dots here are still dirt particles that would not come loose, even after flashing it a couple of times. All right, and now I will go to the experimental result of growing the antimony onto the silicon. I have two movies to show. In the left one, which is at 750 Celsius, we grow antimony onto the silicon, and I will show the diffraction, what happens with the diffraction image. So if I click now. So if we start the growth, then we can see here that we first have the square root 3 spot, and then also the 5 square root 3 spot that starts to appear. And now the next one is a bit fast, but basically what happens if we lower the temperature, and for this particular experiment, we also increase the laser power a bit, so it's a bit too fast now. But what happens is that here really only get this 5 square root 3 by 5 square root 3. And here we get a square root 3 pattern, but afterwards when we deposit more material, it, it goes into amorphous, grows amorphous, as in we don't see the square root 3 anymore, and also this central order diffraction peak is become much more diffuse. Um, and then, so basically, depending on the temperature, we see different reconstructions form, and if we grow more, then it at lower temperature we can actually grow more and it sticks. Then it forms more amorphous. So we have found three surface reconstructions basically. At 750 C we have this 5 square root 3 by 5 square root 3, and at this one at 700 C we can see this square root 3 pattern. And at a lower temperature, we found another one at a very diffuse spot that can be seen over here slightly, is a 2 by 2 pattern. Very diffuse, but it's still a little bit visible. So the Lean can do this in diffraction, but we can also take real space and see what happens there. Um, so here, I basically do this again, but then we grow it at 580 C, but heat it at every 5 pulses or so. We heat it to 800 degrees very shortly so that the antimony is not absorbed off yet, but it allows the surface to reconstruct itself into the square root 3 pattern. So at 0 pulses here, we see the 7 by 7 reconstruction and layers. Sorry, the surface that we also showed in the bigger overview image. And then here is the diffraction image. And if we go to the right, we add some more POV pulses, and we see that the surface changes a bit in domains slowly into this 3 by 3 reconstruction, or square root 3 by square root 3 reconstruction. Although if we continue too far, we see that it grows further amorphously. And also what we can do is evaporate this back off again. I was maybe not super clear about this, but the antimony basically evaporates off at like 750 degrees. It already evaporates off, but at 800 everything goes a little bit more quickly. So what we've done here is basically we took images before, during, and after this evaporation of the antimony. And what we see here is that on the left we have amorphously grown antimony, and here in the middle, well, we see that we see that the square root 3 pattern is forming into domains. We also have to have a diffraction image there, but I don't have the exact moment to show you here. But then after evaporating it off and we go back to this 7 by 7 reconstruction, there's still left are these shiny dots, I would say. And what I think they are is basically antimony clusters that are left in the surface. If we heat up further, like to 1,000 degrees or so, then also these shiny dots are removed again, and we have renewed the surface basically. If we leave these clusters on, sometimes they grow a little bit bigger. And what we can do then is we can do spectroscopy on these clusters. And so here I've shown a movie where the blue, orange, and green is now are these clusters that sometimes have a big contrast with the rest of the surface. And then in red is the silicon 111 response, basically in red curve here. We can see that this is really a different material, as in the spectroscopy curve is much different. So to conclude my results on this antimony growth of silicon 111, it's actually quite a complicated system, and but we have seen some of these diffraction patterns, the 5 square root 3 by 5 square root 3 and square root 3 by square root 3, and also a 2 by 2 diffraction pattern. And the main reason why it's so difficult to get to these reconstructions is that at these temperatures, desorption actually plays a big role. Antimony is continuously desorbed from the surface, while it can also go into these reconstructions. So you need to strike a balance between adding enough antimony continuously to it, and also having the temperature high enough so that these reconstructions actually form. So in red, I have tried to draw some of the lines that are that we have I've shown in the images. Um, yeah, and so it's a bit of a difficult balance to strike. And with a thermal evaporator, you can basically have a continuous flux of um, of uh, antimony to the surface without it disturbing the lean capabilities. But at the lean, there's a very big electric field between the lens and the sample. So if I do POV, which is not a thermal evaporator, but would give a plasma plume, I basically get ions everywhere, and I get a big arc if I try to do it at the same time. So I turn off my lean, I do a couple of pulses, and then I turn back on the lean to actually do these measurements. And that way, it's very hard to get these exact reconstructions. In any case, what we've learned from this is that antimony growth works, and now, of course, the step forward would be to grow this on different substrates, and also to add the cesium that would lower the work function enough so that we can have an actual photocathode of this material. So I have, let's see, we have done some PLD growth already on graphene, where here I show a couple of different layers of graphene. Here you can see this interlayer state again. And then after the PLD, we basically see that it has grown amorphous again onto the surface. We have very not so good, as in we don't have a very nice response here yet, but we're still working on this. And then the next step is really to add the cesium, because already our collaborators in Brookhaven have done some experiments with adding cesium to it, and they see that it grows much better and it grows crystalline when you add the cesium to it. And we also need it because it will decrease the work function of the material so that we can actually have a low work function photocathode for ONM. Okay, with that, I would like to conclude, and I want to thank you all for your attention. And I also want to thank my research group, my supervisors, Kent-Jan van der Molen and Ruud Tromp, and my colleagues, PhDs, and the technicians. I also want to thank the group of Thomas Juffman in Vienna, and Mariana Amaro in Prague, and John Smedling's team at Brookhaven National Laboratory.